Our question is, how could you make a buffer from acetic acid? And we want a final concentration of 1 mole per liter. Well, the first thing that we need to do is to write the correct equation. So the correct equation to understand a buffer for a weak acid or base is its dissociation equation. And we're going to use a Bronsted-Lowry equation here. So we begin with acetic acid. And we show it reacting with water. In equilibrium with hydronium ion and acetate ion. Now we know that the reason why weak acid won't act as a buffer all on its own is because the ionization is very low. Equilibrium lies strongly to the left. Most of the material remains in the unionized form. We need to get some of the conjugate base of the weak acid in order to allow equilibrium shifts left or right and to allow it to act as a buffer. So we have two choices. Number one is we can add a source of the acetate ion. Now, acetate ion is just an ion. We need a compound that contains this ion, which is water soluble, so we can add it to water and provide the acetate ion. So I'm going to choose sodium acetate because sodium is soluble with most anions. So add enough sodium acetate to raise acetate ion concentration to 1 molar. Or the second approach I could take is to start out with twice as much acetic acid as I need, a concentration of 2 mole per liter, and then I need to shift half the material to the right side at equilibrium. So adding a strong base will consume this acid, remove it, and shift the equilibrium to the right. So my second choice would be to begin with 2.0 molar acetic acid and half neutralize it with a strong base. I'm going to choose sodium hydroxide. What this does is it will consume half of the acetate ion, and I drop its concentration to 1 mole per liter. It will shift half of the acetic acid to the right side as acetate ion, and I will end up with 1 molar for the concentration of the acetate ion as well. Even the spectator ion in solution will be sodium in each case. These will be absolutely identical after I've finished making them. It doesn't matter which path I take to get there, the result will be exactly the same. This time we're going to make a buffer from ammonia, which we know to be a weak base. Once again, the approach is the same. I need a dissociation equation, and I'm going to choose to use a Bronsted-Lowry equation. So I need ammonia, NH3, reacting with water in equilibrium with OH negative and NH4 plus. This will allow me to figure out the two components that I need to make my buffer. Once again, they're not two reactants, it's two components in the system. They actually come from opposite sides of the equation. I need some ammonia, and I need some of its conjugate acid, the ammonium ion. So I have a similar problem as in my last example. Ammonia, being a weak base, does not produce very much ammonium ion. This equilibrium lies very strongly to the left. Very little material resides on the right side at equilibrium. So I need to add another source of this ammonium ion, or to make it somehow. And again, I have two options. My first option would be to add ammonium ion directly from another source. I can't add more ammonia because it simply won't ionize. I need a water-soluble ionic compound that contains this cation. So I'm going to add sufficient ammonium ion by adding ammonium chloride. So in the last example, I used sodium as my extra cation to get the compound. Now I'm using chloride. Just remember these as the two ions in common table salt. Add ammonium chloride until the ammonium ion concentration is 1.0 molar. The second way that we can do this is to begin with the ammonium ion at twice the concentration needed and half neutralize it with a strong acid. If we add a strong acid, it will consume the hydroxide, shift equilibrium to the right in a Le Chatelier shift, and generate ammonium in the process. If I neutralize half of this, half of it will have disappeared, and half will end up in this form. So I can begin with ammonia at 2.0 molar and half neutralize with HCl, hydrochloric acid. Any strong acid will do, but by choosing HCl, I will arrive at exactly the same solution. Again, even the spectator ion, which is the chloride, will be the same in these two solutions.